All right, what up, dudes? Okay, so I want to show you folks a little bit about the assignments that I'm making. For those of you who came in and actually did a lab with me, I apologize, but I decided to change it up on you. It's not necessarily that I apologize, it's just I discovered an easier way to do it, and so I wanted to do this. I would like to use the 3D printer that Myron B. Thompson Academy has, and I think it's amazing. It's an amazing project. So, what I did was, no, it's cool. We have a 3D printer, but I'm being told that we have to be very careful exactly with how we use it. So, I, all I'm doing with you folks now is I'm asking you to build a 3D model, which is not to say for sure that we're actually going to get to print this 3D model, although I think it'd be good. How are you supposed to turn in the flashcards assignment? Alana, right? I have an idea for that as well. I'll show you. Okay, so Alana, got it. Let me show you the periodic scaling assignment first, and then I'll show you the other one. I actually think I did a really good job at uploading a YouTube video for the instructions. So make sure you watch that because it's awesome. And, I uploaded this over the weekend. But watch the YouTube instructions and it will show you exactly what you need to do. Here is the periodic table that I built. Okay? And what I did was I decided to have each person do a specific periodic table thing in the periodic table. So what we're going to do is we're going to play with this 3D model. Edit in 3D. I think that's all you click. You click Edit in 3D. And it will open up the periodic table for you, and it will probably take a long time to upload because it's a pretty big file. And here's what I'm going to hint at for you. I don't know how to do this. I don't know how I would do this, to be honest with you. But I don't even think that I don't even know if they'll print it up. I sure hope that they'll print up this thing for us. I checked, and if I were to order this as a 3D model, it would cost me like $102. I'm not going to pay for that. But what I would want to do is maybe they might print it up is if A, we shrink it, and B, it uses less material. So the less amount of material we could use, I think the better chances are of them actually printing this thing. Does that make sense to you? How did I do what? Oh, I think I just pressed Edit in 3D from the thing, and it opened it up for me. So I can zoom in, I can zoom out. I think that I can hold Control button and move the model around, that kind of stuff. And so I give a pretty good explanation as to what it is you need to do for this thing. How did I do what? What are you talking about? Oh, how did I make the table? By hand. It was annoying. It was horrible, horribly annoying. But I did it because I like you guys. Yeah, I just did it. Tejas, your microphone's not working. All right. Anyway, that's how I made it. I just made it by hand. It was a pain in the butt, and I just grouped it all together. So now you can now instead of having you folks build a periodic table, all you gotta have to do is augment mine. Sound good? And I explained to you guys how to do it. All you do is just kind of like, no, wait, that's wrong. If you want to make this thing taller, you would use this arrow right here. It's this little button right here, and it would just, you can choose the height exactly that you would want it at. I think I have you turn it to that level, and that way you can edit this thing and see exactly how high you want to make those things. And then you want to move the tile. Oops, whoa, zoomed out. You want to move the tile to go right on top of that. So then you use this little triangle thing, and that moves it up and down. Like that. All right. And then here's what I'm going to say is I have no guarantee that they will let you build this thing or that they will let us print up this thing. But what I am going to say is that all right, I have no guarantee that they're going to let us print this thing up, but maybe if you make a really nice one, like maybe I'll print up one of your models and I'll print up the nicest version of the model. I'm also going to print up the one that uses the least amount of material. So one of the things that I was thinking about, and I don't know if you folks want to do this, maybe what we should do is before I do this, I think what I could do is I can, let's see, I want to make a hole. Okay, let's see. I'm going to go here. I'll put in a hole right here. There we go. I'm going to make it smaller. Got it. Then what I'm going to do is I'm going to make it a little bit smaller than that. Like that small. And then what I can do is I can move it right here. And then grab both of those things and like combine them. So now I have, instead of a solid block, I have a hollow block. You folks can figure that out. I'll let you folks play around with it. But if you guys can use the less material you use, the better chance it is for us to actually get these things printed up, which is exciting to me. It's an exciting prospect. So anyway, this is your periodic table assignment. Any questions about how to do this or what to do or any of that stuff? Are you excited about this? Okay. I had some people having trouble with uploading their stuff to our chat or to our discussion. So I think that what instead of uploading the actual file, maybe upload the link. So I'll let you guys figure that out. But I have kind of an introductory assignment, which is worth 10 points. And basically, I just want you to create something creative and upload the link for that. Sound good? Yes, no, okay. Which I wonder if anyone... No, you don't have to create a table at all. I already did it for you. Oh, cool. Let me take a look at this. I'm just curious to know what it looks like now. I created it for you. All you got to do is modify my table. Yeah, no, it's a... Ooh, wow. That's awesome. I like it. Oh, wow. Cool. Yeah, I know. It's great. Yeah, awesome. Okay, cool. Let's get started on chemistry. So that's the assignments that's coming up. Here is some algebra, which is not something you folks are interested in. Let me get started on chemistry. Don't save. All right. Here's what I want you to do, and I'm going to do my camera real quick. Can you folks see my face? You might need to like minimize the desktop sharing. All right, give me a second. Hold on. So I haven't finished making my flashcards, but here's what I want you to do. I want you to do the first 52 or 54 or however many you can fit flashcards. And they look kind of like this. I basically just got a deck of cards, and these things print up to be about the exact size of a deck of cards. And I took tape, and I put tape here and a tape here. On the back of these things, I'm going to put an N. So I'm going to take a little Post-it and put an N right here. I want you folks to make the flashcards, but I didn't put a due date on it. And I'm going to show you what I want you to do with it. What I want to do is I want you guys to record videos for me of you folks going through all of your flashcards. Because you need to, there's no good way about doing this. And so I'm going to ask you to record and submit a video for me of you folks doing stuff like this. Like, what is this? This is nitrogen. Sulfur, xenon, iodine, bromine, and it's going to be kind of a competition. We're going to see who can do it the fastest. Which one of us can do it the fastest? So you guys are going to record like videos for me, and then you guys are going to go through and see if you can go through all of the flashcards as quickly as you can. All right. So what do you do with the Pokemon cards? The Pokemon cards, save those for a later assignment. I'm going to be giving you that stuff. I'm gonna be turning that into a quiz, and it's actually a really fun quiz. All right, I'm gonna get to that, but that's not what I want to cover today. Today, I need to finish off on talking about nomenclature. Got it? So, define fun. All right, fine. I'll tell you what. It's Mr. Dalday version of fun, which for students, they never say, oh, that kind of fun. Yeah. So it's fun for me. No. I'm going to make it so that it's fun for you too. Okay? Look, it's not... All right, go back to the desktop sharing. Look, here's the bottom line. It's not Mr. Dalday versus you. I'm trying to make this thing as interactive and fun as possible, and make it interesting and all of that kind of stuff. So, I'm really going to try to make it so it's actually like interesting to you and fun, and you actually learn something. That's what I want to do. All right. So fun to me is the stuff where you learn. Got it? Mr. Dalday isn't out to get you, or at least I hope you don't think that I am. All right, let's talk about nomenclature. And I feel like this chapter 2 covered nomenclature in the last third of the chapter, and it was so quick. It's so like, whoa, where did that come from? We talked about the periodic table before, and the periodic table kind of looks a little bit like this, kind of like that, right? And then we said anything in this group right here, that those guys like to form, what are they called? They're called cations. And they like to form +1 cations. Right? Because they have one, They have one too many electrons that they have to deal with. So they want to get rid of those electrons. And over here, these guys are noble gases, so they don't like forming anything. They don't like forming positive or negative cations. They just like staying the same. They don't form ions at all. Does that make sense? They don't like giving up their proton or their electrons or taking in more. Right. Over here, these guys form -1 anions. Anions are ions that are negative. And then over here, these guys like forming +2, and so on and so forth. And over here is -2. So here's the anion side. Here's the cation side. And then for the most part, I think that the transition metals, they like forming cations as well. Are we cool with that? Okay, so nomenclature. When naming a binary ionic compound of type 1, it's pretty straightforward. all you do is you look up on the periodic table where the element is, and you slap the name together. For example, let me do an example. How's about ALC3? ALCL3. Okay? All right. In the textbook on page 61, there's a table, and that table gives you this list of common cations and anions that these things form. Let me see if I can download that table. By the way, great job, Alana. Okay, let's see. Can you folks still hear me? Is the audio coming out right? Okay. Which I can't promise you that we'll print that up, but I'd sure like to send that down to the thing and show them. Look what my student did. Aren't they amazing? Okay, here we go. Here's what I want you to do as well. And I'm going to ask you to do this later on or in another assignment. Is if you look on page 61, I want you to download this, or I want you to okay, wait 1 second. My computer's still a little bit slow. It's pulling it up. All right, here we go. So here's page 43. Here we go. All right, this table right here. See this 2.3? This is a really important table for you to memorize. So on a new separate piece of, on a new deck of cards, I want you folks to start writing out these flashcards. Like magnesium has a +2 cation that it makes. If we look over here, ALC3 is what I had written up over here, ALC3. Aluminum, you look at that table over there, and aluminum always makes a +3 cation. So Al is right here, and that usually makes a +3 cation. Cl is chlorine, and if you look up where chlorine is on a periodic table, if you look up where chlorine is, let's just look it up real quick. Chlorine is right here. Sorry, my computer's laggy just a bit. There we go. Chlorine is right underneath fluorine. It's got 17 protons, and usually what it has is one extra electron. So it makes a -1 compound or ion. And the reason why it makes a -1 is because everything in group 17 makes a -1 ion. Or yeah, it makes a -1 ion. And we talked about why that is. So Cl makes a -1 anion. And then what you do is you basically write this out as you'll need 3 chlorines to make 1 aluminum, to match up with that 1 aluminum, so you can balance that out. So if you want to write that out, this is called aluminum chloride. Yes, exactly, aluminum chloride. All right, so that's type 1, and I'll be honest with you, type 1 is a little bit uninteresting. I mean, it's just pretty straightforward. Got it? Here's the tricky part. When we get into type 2, all right, whenever we're dealing with cations, those are the ones that make positive ions. If you're dealing with things in category or in group 1 or 2, those always make a +1 cation or a +2 cation, and those never change. However, there are some transition metals that can make 2 different types of cations. For example, ferrium, also known as iron. ferrium, which is right over, where is it? It's right here, 26. You guys see it? This ferrium, it actually makes it makes two types of cations. It makes a +3 version and a +2 version. And I guess the question that we have to ask ourselves is, which cation is this making? Does that make sense with you? So, like if I had something like FeCl2, okay? How would I name that? Would I call that iron chloride? And I guess the question that I have to ask is, how do I distinguish? Because which cation is this iron making? Well, if Cl makes a cation of -1, right? I'm sorry, there should be 2 down here. If Cl makes a cation of, or an anion of -1, then obviously FeCl2 means you're dealing with the +2 version of iron, because you'll need 2 Cl's to balance that out. Does this make sense to you? So the type of iron that I'm dealing with is iron 2 as opposed to iron 3. That's the type of cation that I'm dealing with. And we use a Roman numeral to kind of identify that for us. Whereas if I had something like FeCl3, then I can look at that and say, okay, well, Cl makes a -1 anion, and it needs 3 of those to balance out with that 1 iron. So the iron in this particular one that I'm trying to deal with is iron chloride, but the iron is of version 3. Or, yeah. Do you folks see this conundrum that we have? Did I confuse you or what? What's going on? Can you guys hear me? All right. So, there are certain cations that you have to be very careful with. If the cation is in this column right here or this column right here, if we're talking about 1 and 2, then those ones you don't have to be careful with. This one always forms a +1 cation. This one always forms a +2 cation. But if you're dealing with something like cupric, which is also known as copper, or cuprium, I think it was. It used to be known as cuprium, which is why it's Cu as opposed to, so it's copper. This one can form either a +2 or a +1 cation. Or if you're dealing with cobalt, which is Co, that's this guy right here. This guy can form either a +3 or a +2 version of himself. Does that make sense to you? Or if we're dealing with Sn, better known as tin, tin can actually form a +4 or a +2 version of themselves. And so what's the best way to go about doing that or memorizing that? Well, I would make flashcards for table 4. And I would make a flashcard on one side that says iron can be either +3 or +2. And you would just have to memorize this. Got it? So let's go through a few examples and we'll see what we got. So, what do I want if I have manganese 4 oxide? There's the, let's see, manganese 4 oxide. There's the name of it. I want to know what the formula for that would be. Okay. What I would do is I would say, all right, manganese 4 oxide. Manganese, Mn. What's nice is I actually tell you the charge on it. It's Mn plus 4. If it were manganese plus 3, I would put manganese 3 oxide. Does that make sense? So I've already immediately told you the charge on the manganese, the ion that it makes. And to balance that out, I would need my oxygen. Now oxygen it likes forming a -2 version. So in order to balance this out, how many oxygens would I need to balance out my 1 manganese? And please answer if you can hear me, or if anyone's still there. Five? No. You'd need 2. Because if you had 2 oxygens, that would make this -4 overall charge, and then that would cancel out with my +4 overall charge. So if you wanted me to write down manganese 4 oxide, this is the equation I would write down. MnO sub 4, O sub 2. Does that make sense? I'm actually teaching you the easier version of this stuff. We used to have a convention where, or here, I'll explain this to you in just a second here. How's about this? Lead 2 chloride. All right. Lead 2 chloride. What I'm going to do is I'm going to look up what chloride likes to form. Chloride comes from chlorine, which is right here. It looks to me like it always likes to form a -1 ion, or anion. So Cl -1. I know that the lead I'm dealing with, Pb, is +2 version. Got it? So I'm going to need 2 chlorines to balance out with that +2 thing, because chlorine naturally only has -1. So the equation I would write is PbCl2. Because I need 2 chlorine ions to balance out with the lead 2 version. All right, here's a quick note. I'm actually teaching you the easier version. I actually learned it when I first learned it. I learned it the hard way. And the hard way is whenever you have these two, like these elements that have 2 possible cations they could form. For example, Pb +4 and Pb -4 or +2. What the new names for those would be lead 4 or lead 2. That's the version I'm teaching you. The old way, we used to have to say, okay, if it were the bigger version, then how did that go? Okay, wait. If it were the bigger version, then you would name the word in ik. And if it were the smaller version, you would name it in us. So this would be plumbumic. And this would be plumbumus. And for this old convention, you would always have to use the original Latin name, not the new English cool name that we use. So I'm not having you do this. But technically, if I ask you, or I mean, technically, what the questions used to be like, what is plumbumic or chloride, or what is plumbumous chloride? This would be lead 2 chloride. Does that kind of make sense? Yeah, exactly. For iron, you would be dealing with ferric or ferrous, like ferrous oxide or ferric oxide. And depending on how that word ended, you know, based off of the old original name, it would denote a different thing. But we decided to make things easier and just incorporate these Roman numerals. So if you're talking about lead 4, you would actually write lead parentheses with a little Roman numeral 4 after it. Versus lead 2 would be lead 2, literally. Does that make sense? Okay. Now, type, if you look at the textbook that we have, it actually shows you a little table or a little periodic table with the common cations that it forms. So you notice that everything in group 1 always forms a +1 cation. Everything in group 2 always forms a +2. Whereas these ones over here, like iron, forms a either +2 or +3, and you have to denote which one it is. Or cobalt forms a +2 or +3, you have to denote which one it is. Some of these metals over here, like for example, even though silver, which is Ag, can form other cations, it almost never does. I've never seen, oh no, not silver, I'm talking about aluminum. Even though aluminum can form different cations, it always, in every single element I've ever seen it in, is +3. So I think that in that specific case right here, we don't even bother with, you know, having to specify in Roman numerals that we're dealing with a +3 version. So anything over here is anything in green is the type 1, where all you have to do is just kind of write the name, like silver hydroxide or something like that. Does that make sense? Yes, no? Okay. Polyatomic ions. Now this one's a little bit, all right. Here's where I'm going to kind of leave off. Some of these polyatomic molecules, like for example, if I were to write out ammonium nitrate is written out like this: NH4 NO3. Okay? All right. Yeah, you can leave, but I'm going to finish off. All right. NH4 NO3. I'm going to finish off in 5 minutes. NH4 NO3. This is ammonium nitrate. Ammonium nitrate. Okay? Now, ammonium nitrate, this, if I were to write this out, NH4 forms a common cation of +1, and an NO3 forms a common anion of -1. And so those together form ammonium nitrate. This alone is called ammonia, or ammonium. And this one over here, this is called nitrate. And there's only one way to really get good at knowing these polyatomic molecules when you see them. And the best way, or polyatomic compounds when you see them. And the best way, really, and I'm going to make you do this, is make flashcards for this table. And you need to memorize this. This is kind of the bane of chemistry, and I'll be honest with you, I didn't like chemistry until I finally sat down and actually just memorized it. Chemistry was always really hard for me until I finally just sat down and just be like, all right, I'm going to memorize this. And I made flashcards and I practiced it, and I got really good at this stuff. But before that, I hated chemistry. So if you're finding yourself hating chemistry when I'm asking you for these nomenclature things, it's probably because you didn't take the time to memorize it. And the best way to do it is just to do it. I don't know how you memorize things, or if you spin on your head or stand on your head or whatever it is. Anyway, get out of here, folks. You guys have your class. I'm going to probably do a lot more examples on nomenclature on Wednesday, and then on next week I'm going to start chapter 3. Got it? And I think for lab we're actually going to make s'mores and Kool-Aid. So bring marshmallows and chocolate and all of that kind of stuff. All right. Okay, bye. Celeste, for lab, I'm going to make them make s'mores for next week chemistry lab.
Yes.
Because we're doing stoichiometry. But what I'm going to do is I'm going to give them like weird numbers of graham crackers and weird numbers of like chocolate bars and stuff like that. And I'll just be like, make as many s'mores as you can. But a s'more has to have 2 graham crackers, 3 marshmallow or 3 chocolate bars and 1 marshmallow.
Okay.
And then they're gonna. I mean, then the problem is they're gonna have limiting reagents, right? They're going to be like, well, I can't technically make this many s'mores because you only gave me 5 graham crackers.
Yeah.
You know, well, that's a problem. You know what I mean? So.
But you're going to start breaking graham crackers in half.
Yeah, but you can't do that with molecules, right?
Yeah. Ooh, that's a good one.
So I'm going to make them make s'mores, and then I think what I'm going to do is do one where we do Kool-Aid. Is titration? Titration I can't really do until I cover pH, though, yeah? I mean, titration is kind of another... I feel like titration I haven't gotten to yet, because I've just finished nomenclature and periodic table. So next we're going to cover stoichiometry. Oh, wait, I didn't even stop my recording. I've been recording our conversation.